So this is our first speaker, Grace Shore, who's going to talk about variability of bright material in North Polar Layer deposit craters.
Thank you for saying that very long title. Okay, it's really great to be here, especially among the crater experts. So I have a whole slide that is just questions for you, and I would love to have every single one answered. I'm a postbac researcher over at LASP with Margaret Landis, who is a frequenter of this conference, though she couldn't be here today. She is moving to her new faculty job at ASU. But I'm going to be presenting some really exciting results of this near Martian decade of observations from the HiRISE camera on these icy North Polar craters. So just in case people aren't super familiar with the North Pole of Mars, there's this area that I've been looking at, and it's called the North Polar Layer Deposits, or the NPLD. They are kilometer scale sequences of water ice, and it has varying dust content. This region hosts a seasonal CO2 frost cap. It deposits an appreciable amount of CO2 from the Martian atmosphere during northern winter, and then it sublimates away during northern spring. Now, the currently forming layer of this polar layer deposit is called the Northern Residual Ice Cap, or the NRIC. There's a few different names for it. This is just the one I'm going with. It's about 1 meter thick, and it should be in solid vapor communication with the atmosphere. Now, what makes this region so exciting for us to study is that it potentially contains a climate signal buried within the NPLD. If it's readable, it would give roughly a 5 million year long history of the Martian climate, and it could reveal Mars that most definitely looks very different than the one we see today. So it would link the current observable climate to the past if we're able to decode it by looking at current surface features. Now, some previous research has shown that this is kind of a uniquely young surface. The Banks et al. And Landis et al. Studies used crater production functions to show that there's a relatively young surface age. And then Andrew Wilkowski and Paul Haynes said, no, we got to model this. And went with the landscape evolution model, and it also showed that this young surface, or that this surface is kind of uncharacteristically young. Now, this graph from the Banks et al. Paper shows a lot of craters in this catalog that were originally looked at, whether they had ice in them or they didn't have ice in them. This is the data set that I pulled from. So the Banks et al. Team was the one who originally got these crater sites together. So there's some contradictory analysis on what this currently forming cap, or the NRIC, is currently behaving like. Some ice grain measurements suggested that larger ice grain ice is being exposed, so this ice has had enough time to sinter, become larger, suggesting that net ablation is occurring on the NRIC. But from the same study, they found the NRIC to be relatively dust-free. So this could mean that the current surface hasn't had time for airfall dust to accumulate. This also could be due to katabatic winds, but this would suggest a younger surface age. So there's a little bit of tension with understanding what the current regime is on this surface. So this main question we're looking at is the NPLD gaining or losing mass today? Constraining the mass balance is really important for understanding past climate variations, because it would provide a link to the current observable climate and past accumulation rates. And why we look at craters is because in those previous studies that I had shown from Landis and Banks, the ice deposits within these craters have shown to change possibly centimeters per terrestrial year. So this is a potentially measurable rate. So when we're looking to constrain the mass balance, these craters offer a really prime target to look at. So within that larger question of the NPLD mass balance, I'm trying to answer at what rate are these NRIC craters being filled by water ice? And given the unique thermal environments of these craters, what could this imply for the non-crater terrain? And as a whole, what the mass balance is of the NPLD? And especially with these unique thermal environments, I'm looking to you guys to help me answer this one, because I am not a crater expert. So my data set that I looked at had 41 of the ice-filled craters. So this is a more cut down version of that first graph that I had shown you. This totaled 35 sites, crater sites in total. These sites encompass either one crater or a crater cluster. And we had 228 high-rise images. The high-rise spacecraft offers really insanely great resolution of these craters. They're about like 30 to 70 meters, so they're pretty small craters. 228 of these images span Mars year 29 to Mars year 37. Currently, the Mars year 38 campaign is being conducted right now. So 9 of these sites already have a pre-existing high-rise digital terrain model and the interannual coverage. This is really going to be used for a quantitative study. That's coming kind of later on. The remaining sites do have interannual coverage, but they don't have a DTM. But this is still used for context, and this is used for more qualitative study, which is the results that I'm sharing today. Now, to expand the quantitative study, 11 of these sites already have stereo pairs. So this makes the generation of a DTM possible in the future. So I will be bugging Sarah Sutton over at U of A for those at some point. Now, I couldn't go through this presentation without showing some of the lovely craters. So as you can see, these craters do not look the same. We weren't characterizing them necessarily based on if they had like a fresh rim or anything like that. They have crater clusters. They have not necessarily like radial deposits. This one has given Margaret and I so much trouble. We call it the Bride A crater. I don't really want to talk about it, but I just felt like I had to show it. So while these don't look the same, what characterizes this group of craters is that there's some sort of persistent high albedo bright material that is persistent across multiple Mars years and is a higher albedo than the existing terrain around it. So that's kind of what is linking all of these. Now, Colin Dundas has been kind of harping on us saying, but what if it's not water ice? And we were like, no, it is. And he was like, do you have the proof? And we were like, no. So we got the proof, and it is water ice for at least the 3 craters we sent to him last week. Some folks over at DLR in Germany used this 3-point spectral analysis, looking at the spectra from within the crater at the icy deposit, and then outside of the deposit, but still within the crater. And the spectra is consistent with water ice, which we knew the whole time. This is just another graph showing that these were the 3 crater sites we observed. And from water ice poor to water ice rich, they all fell within that water ice rich category. Now, we only did it for 3 of the crater sites. The spectral analysis required the crater to have some specific lighting conditions and also be within the color strip. So we didn't submit every single crater. Also, this was done last week. So we could only get 3 in time for this conference, but all of the bright deposits share the same characteristics as being persistent and higher albedo than the rest of the terrain. So we're just going to say, for the sake of sanity, that the rest are also water ice that we're looking at in this study. So there was kind of 2 methods of mapping. There was the mapping with DTMs. This is for more of the quantitative mapping. And then there's this qualitative mapping that encompasses images that have a DTM and or sites with a DTM and sites without a DTM. So first, I'm just going to briefly go over the mapping with the DTMs. This was some work kind of setting up for the modelers to use. So I used ArcGIS Pro, and I traced the perceived border of these ice deposits. And in black is where I am like over 90% certain this is where the border is. The red dotted line is this could be reasonably redrawn if another mapper were to look at this.
Question.
Yes.
How sensitive is your final analysis to being 2 pixels off?
Right. I can't give like a number on that. The hard part with this and where the largest uncertainty stems from is when I'm initially loading in these images, I have to change the stretch quite a bit in order to see the deposits. So when you're changing the stretch even a little bit, those pixels will change in the amount in the on how bright they are. So this is basically like as best as we can tell with as clear of a stretch per the mapper. So this is definitely not the best way of mapping the ice deposits. Well, actually, this was the best way that I found. If there are other ways, that's also another thing that I would love to hear, because a lot of these changes could be happening on the order of 1 to 2 pixels, but it's really hard when you're trying to change that stretch to even just see where a border could be. But we did our best to try to distinguish between the sharp edge central deposit and the surrounding bright diffuse material, and bringing in the office that I'm at. There's grad students in the geology department who do maps for like their living. And it was kind of working with them, and it's like, does this seem like this could be replicated by you? And it's like, yeah. And we went, sure, cool. But what these shape files with the borders are going to be used for are they're going to be handed off to some modelers. So Shane Byrne and Sarah Sutton are performing right now a first order volume change calculation. Now, the way they're doing this is one of the sites that has a DTM. They're deriving the ice fill volumes by assuming a parabolic crater shape that does not change from Mars year to Mars year. And they're also assuming that the ice levels rise and fall evenly. This isn't really what we see at all, but this is really just to get a first order approximation. And we didn't have time to get results for this conference. But hopefully in the future, you'll probably see some work by Shane or Sarah looking at that. But this is like the model that we're looking at. This is going to be Andrew Wilkowski's model over at JPL. So the images with the available DTM and the ice lens border, he has been working on this coupled thermal and vapor diffusion model that really explores ice accumulation rates and ice stability and the thermal properties within these craters, or within sort of a lot of different types of geological features on Mars. And it's in an effort to constrain the atmospheric water vapor densities close to that NPRC or NRIC surface. So just that currently forming layer. So that's still in development right now. And he will be coming out with a work with that probably within the next year or two. So that was just really some preliminary work. My work focuses more on the qualitative mapping. This is going to be used as a check against those model results. So if I'm seeing, a site that, oh, look, there's an increase happening, and then the model results are saying there should be net ablation occurring, then, which is what we have sort of found in the first few runs of the model, there's some physical property that we're missing in this model to account for these changes. So this is just one of the example sites, site 17. This is one of my favorite sites. It's a crater. It looks like a crater. It's great. So this is from Mars year 29 to 37. The Mars year 38 image should be coming out in the next couple weeks. I'm really stoked for that. So we're seeing a show of accumulation between these two Mars years, just to focus in on them. I'm considering this accumulation because we see in this left quadrant with the grid overlaid, it's really easy to see that accumulation happen. Now, one thing I want to point out is the L sub S, or solar longitude. It's just the way we tell time on Mars. This can alter results because if you remember, I said the North Pole hosts that seasonal CO2 frost cycle. Now, we did that spectral analysis to confirm that these deposits are water ice. but we can't see like at every single point in the crater how much of this is water ice versus how much of this is CO2 frost. Now, LCBS 130, the CO2 should have sublimated by then. LCBS 113, not so much. It's usually around like LCBS, I want to say like 120, varies Mars year to Mars year. That's when the full sublimation occurs. So could part of this accumulation be frost? Maybe, but we don't really have a good way of going through, every point on this and seeing the difference. But if you guys do, please let me know. That would be great. We also see, again, a really sizable accumulation occurring between 36 and 37. Again, LCBS 103, could some of this be frosted? We can see some of that CO2 frost around the terrain. So it's really what fraction of this is water ice accumulation versus CO2 frost, kind of obscuring our view. For all those people who are like, well, what about decreases? We got those too. A lot less of them, but we got them. This site was really interesting to look at because between Mars year 34 and Mars year 35, these two images, a global dust storm occurred on Mars. So we see a lot of this dark material. It was probably because of the dust storm blowing in. But we also see the rim of the actual ice deposit shrink significantly as well. So there hasn't been any work done yet, but I would be really interested to see the effects that global dust storms have within these craters and within the microenvironments of these craters. I think that could be a really cool topic for future work, and especially how it affects the water ice. So this is a site, so the previous site I had shown was site 17. It was used in this qualitative mapping study, but that site also had a DTM. This site does not have a DTM currently, but we see both increases and decreases. We see a decrease in the ice lens between 34 and 35. Again, how much of this is CO2 versus water ice remains to be seen. We also see increases here. If we assume this to at least in larger part be a water ice change versus CO2 ice or CO2 frost, I would say this would make a great candidate for future DTM production because we're seeing appreciable changes happen within these. So another point of this mapping study was what sites should we target for future DTM generation? And the schema I kind of adhere to was if I'm seeing changes, because some of these sites exhibited no change, but if these sites without a DTM exhibit some sort of change, especially both increases and decreases, I think that's a good rationale to at least look into getting stereo pairs so DTM generation could be possible. This was another just fun crater to look at. These changes, a lot of the times we're seeing are not radial in nature. We're not seeing, this perfectly circular deposit that goes up and down throughout the Mars years, but instead there could be like local regions of water ice popping up or CO2 frost. It's water ice. But with these new deposits forming in distinct areas, I think this really points to the unique thermophysical properties of these craters and how are these thermophysical properties different than the non-crater terrain. So overall, we saw that if changes were to occur, they were net increases in the bright material. And we did see decreases across 4 of the sites, but we only observed them after the Mars year 34 global dust storm. Now, we started this imaging campaign in Mars year 29. There was also a global dust storm that occurred in Mars year 28, but we don't have images from before that. So we can't exactly say whether the Mars year 29 images were influenced in any way by the dust storm. So this is one of those moments where it's like, 2 decades long of data would be awesome, but it's done a really good job. And we also found smaller craters appear to preferentially experience accumulation changes. This kind of makes sense because if a small crater exhibits a change, it's usually easier to see than a large crater exhibiting a small change. So that's also just kind of up to the mappers. So overall, we found more sites exhibit net accumulation. So these crater environments could be gaining mass because of this. Some of them had really large accumulation changes. So this could signal a broader accumulation across the NPLD, which would suggest that we're in a climate regime currently on Mars that has enough water vapor circulation to support localized water ice deposition at this moment. It also could suggest that the NRIC is representing an actively accumulating surface. This agrees with the Landis et al. Conclusion as well in their work. Or there could just be this preferential accumulation happening within the craters, which could signal a shorter crater retention time with this preferential accumulation happening and kind of wiping out surface features faster. Now, for the group, I promised you a question slide. These are all the questions that I would love some crater experts to chime in on, answer, or have a framework on how to go about answering these. A lot of my work has been on avalanches on the North Pole, so craters are not something I am super well versed in at all. But I would really love to know, especially if there's any age-dependent morphological features that could correlate with accumulation patterns, if there's any sort of data that shows like older craters could preferentially lose or retain ice based on erosional states or anything like that. I'm not sure how much time I have left. I wanted to kind of, okay.
5, 7.
Okay, perfect. Before I'm going to leave it on this slide, but before I do that, I want to say this work is going to be submitted to GRL, and the next couple weeks it'll be my first authored paper. So thank you. So if this presentation you were like, oh, I want to read more words on that, stay tuned. So I'm going to leave this up here, and I would love to take any questions, but more so I would love some of my questions answered. Okay, thank you.
Thank you.
So did you use the very first Mars data sets that included the MAUD instrument and the IRTM from the Viking orbiters and the weather data from the Viking landers when you did your research?
No, we only used high-rise images, and any of the atmospheric work or atmospheric data we've gotten from MCS. I know that's what Andrew's using in his model.
That might be data that you would find very valuable because it had the longest data set and the earliest data set.
Okay.
So that you can increase your parameters
Okay.
and find more patterns.
Perfect. Yeah.
I don't usually deal with craters that are this small, but because you're dealing with microclimates,
Yeah.
basically, I'm curious, going on the atmospheric question, have you considered whether localized dust storms or even localized clouds or something could be affecting things such as, have you looked at the Marcy data set? I guess actually it's not really well processed yet. Have you looked at or thought of that kind of thing as a potential process that could affect things? So like, if there happened to be a local dust storm yesterday and you took the high-rise image today, could that have affected your results?
I have no clue as of yet, but I think that's one area that I think going forward is a really important step within this analysis. My work was really just going through all of the high-rise images and getting them into some sort of data set that others can look at. That was my main task. I think this grant was from almost 10 or 15 years ago, and it's on its nth no cost extension.
That's fine.
Yeah, of
So-
course not. But
Get in touch
Yes.
with me, because
Yes.
I'm gonna pimp my work. I
yeah,
have a
come
grant,
on.
I have a grant right now to process all of the Marcy data.
Okay.
And as part of that, I am making every 2-hour with cadence, not mosaics, images of each pole when they're illuminated.
Oh, wow. Okay, yeah.
So that could potentially be a very useful data set for you.
Yeah, I
And
think
it's
so.
at 500 meters per pixel or 600 meters per pixel, as opposed to 30 centimeters.
Yeah.
But you can see cloud movement, dust cloud versus ice cloud, because it's a 7-color instrument, all that stuff that could potentially be useful.
Okay, yes, I will definitely be reaching out to you then. Yeah, especially since we only saw decreases observed after that global dust storm. It would be, because I haven't even thought of the local dust storms. I was just thinking of the global dust. I wasn't even thinking of the local ones, but
And
yeah,
Marcy is on MRO, so if High Rise took data, Marcy took data pretty much.
perfect. Okay, great.
Check, see if there's any questions online. It doesn't look like it. I don't think I'm missing anybody's hands up or anything.
Just a
Okay,
quick
go
chime
for it.
in as a addition, it is still interesting that you are getting net accumulation even like without paying attention to those localized dust storms, like the only like decrease in, is it just brightness or size or?
Size of the
Okay,
item.
yeah, the only
Yeah.
decrease in size you were seeing was from that global dust storm, so
Yeah,
it's still interesting that the accumulation is still like visible even if there were localized dust storms.
right. And now that it has been brought to my attention, local dust storms do in fact exist on Mars.
Really
It would be interested to see from the ones recorded and go back through where I saw decreases happened, how closely tied those two were. So that's, I'm definitely going to take that going forward. Yes.
One more data set that might be interesting, although it's not imaging or IRTM, but is the MAVEN mission.
Yeah.
So the ion stripping data overlaying that might be might be indicative of some causal.
Yes. Okay. Definitely. And luckily CU is pretty strongly tied with that mission. So I can send down
Exactly.
the hall and get some data from them. So that would be great.
I have another thing to add.
Yes.
Lucky you. So one of the very first things that you showed and that I asked about was, what do your effects matter based on 1 to 2 pixels being off? I was thinking, could you just use brightness contours? Because you're using arc, so that should be able to make contours for you in terms of brightness, and maybe that would be a relatively objective way to do it.
Right. I have not looked at that, but now I will.
Okay.
I didn't know about that tool in ARC. When I started this.
Kelsey? Or Sierra? Does Arc Pro make contours of brightness?
Out of any raster. Okay.
And
great.
Margaret certainly knows how to use Arc, so.
Yes, she has made the transition to Arc Map and Pro, a little unwillingly, but
Yeah, tell me about it.
yes.
In the possibility, this is a stupid question. I'm never quite sure what we're dealing with how you distinguish between frost and water ice.
So
I mean,
that's
how do you define that? I mean,
yeah. So the frost will sublimate away by around northern summertime, and we've imaged these craters well after summertime, and those bright deposits still are there. So we're confident that the deposits themselves are not just CO2 frost, because they wouldn't persist for that long. But that is one of the largest uncertainties to me, and I cannot seem to find a way of like a spectral analysis that really looks, like at each pixel to see, how much of this is CO2 frost and how much of this is water ice. That 3-point spectra, which is kind of the closest we found, really only looks at 1 point and then 1 point outside of the crater. So I'm not sure that there's a way to do it, but maybe that could be a grad project. Who knows?
okay, so it's semi-dumb question. That's okay.
Not at all.
All right, I think that is our time, so let's thank Grace again.